To calculate the sum of receptacle ratings for both 240 volt and 120 volt circuits, multiply the rating of each receptacle by the number of receptacles. For the 240 volt receptacles, the calculation is 50 amps times 2 receptacles per pedestal times 6 pedestals, which equals 600 amps. For the 120 volt receptacles, the calculation is 30 amps times 66, which equals 1980 amps. Now let's delve into voltage drop calculations, starting with the 240 volt circuit. The total wire length is 420 feet plus 550 feet, totaling 970 feet. The resistance of 350 mcm wire per 1000 feet is 0.31 ohms. Therefore, the resistance of the wire is 0.31 ohms per 1000 feet times 970 feet, resulting in 0.299 ohms. With a current draw of 600 amps, the voltage drop is 0.299 ohms times 600 amps, equaling 17.94 volts. Consequently, the voltage at the last pedestal is 240 volts minus 17.94 volts, which equals 222.6 volts. Moving on to the 120 volt circuit, the total wire length remains at 970 feet. The resistance of 350 mcm wire per 1000 feet is 0.62 ohms. Thus, the resistance of the wire is 0.62 ohms per 1000 feet times 970 feet, giving us 0.601 ohms. With a current draw per receptacle of 30 amps, the voltage drop per receptacle is 0.601 ohms times 30 amps, which equals 1.803 volts. The total voltage drop is 1.803 volts times 66, resulting in 118.59 volts. Therefore, the voltage at the last receptacle is 120 volts minus 118.59 volts, which equals 1.41 volts. In conclusion, the 240 volt circuit will experience a significant voltage drop of 17.94 volts, which may not be acceptable for equipment operation. The 120 volt circuit will experience an extreme voltage drop of 118.59 volts, which is definitely not acceptable. It is recommended to install a separate 600 amp panel for the new show power pedestals to avoid overloading the existing panel. Additionally, the wire size for the 120 volt circuit should be increased to reduce the voltage drop. Let's break this down further. When dealing with electrical installations, especially in marinas, adhering to safety standards and regulatory codes is paramount. The National Electrical Code, or NEC, provides specific guidelines for marina electrical systems to ensure safety and prevent hazards. Firstly, let's consider the calculation of receptacle loads. The NEC mandates that the total load on a panel should not exceed its rated capacity. For the 120 volt, 30 amp receptacles, it's crucial to calculate the total load accurately. You're right to question whether to convert to volt amps VA before summing the loads. While it's generally good practice to work with volt amps to account for power factor, in this specific case, since we're dealing with purely resistive loads like receptacles, it might not significantly impact the calculation. However, to adhere strictly to best practices and the NEC intent, converting to volt amps is advisable. Here's how you'd approach it. Calculate the volt amps for each 120 volt, 30 amp receptacle. 120 volts times 30 amps equals 3600 volt amps. Sum the volt amps for all 66 receptacles. 3600 volt amps times 66 receptacles equals 237,600 volt amps. Apply any applicable demand factors or diversity factors as permitted by the NEC. Demand factors allow you to reduce the calculated load based on the assumption that not all receptacles will be in use simultaneously at their maximum rating. NEC Table 555.12, as you mentioned, is relevant here. It provides guidance on applying demand factors for marina power outlets. Now, regarding the derating factor of 40% you mentioned, it's not entirely clear what this refers to. The NEC does not specify flat 40% derating for marina receptacle loads. Instead, it provides specific demand factors based on the number and type of receptacles. Refer to NEC Table 555.12 for the appropriate demand factors to apply. After applying the demand factors, you'll have a reduced volt ampere value, which you can then convert back to amps at 120 volts to determine the load in the panel. Now let's address the voltage drop calculation. Voltage drop is a critical consideration, especially over long distances, as it can significantly impact the performance and lifespan of electrical equipment. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To calculate voltage drop, you need to consider the following factors. Firstly, the length of the circuit. Secondly, the current flowing through the circuit. Thirdly, the resistance of the conductor. The formula for voltage drop is voltage drop equals current times resistance. You'll need to determine the appropriate conductor size to keep the voltage drop within acceptable limits. Several online voltage drop calculators are available that can assist with this calculation. These calculators typically require you to input the circuit length, current, conductor material, e.g., copper or aluminum, conductor size, and voltage. For long runs, like the 420 feet to the dock and 550 feet to the last pedestal, voltage drop can be substantial. You might need to increase the conductor size to minimize voltage drop and ensure that equipment operates correctly at the end of the circuit. Now, let's look at the existing panel and the need for an additional panel. Based on your description, the existing 600 amp panel already has 66, 120 volt, 30 amp receptacles connected to it. This represents a significant load, and adding 6 additional shore power pedestals, each with 250 amp, 240 volt receptacles, would likely overload the panel. Your suggestion of installing another 600 amp panel fed from the 1200 amp main to the base of the dock is a prudent one. This would provide additional capacity to accommodate the new load without overloading the existing panel. When installing a new panel, ensure that it is properly sized to handle the anticipated load, with sufficient spare capacity for future expansion. Consider using a panel with a higher ampacity rating than initially required to provide flexibility for future needs. Regarding the existing panel's feeder conductors, you mentioned that they are parallel 350 MCM conductors and that they did not allow for 600 amps during the initial installation. This is a concern that needs to be addressed. The ampacity of conductors must be sufficient to carry the load they are intended to serve. NEC Table 310.15b16 provides ampacity ratings for conductors based on their size, insulation type, and installation conditions. You'll need to verify that the existing 350 MCM conductors are indeed adequate for 600 amp load, taking into account any applicable derating factors for ambient temperature, conduit fill, or other conditions. If the existing conductors are undersized, they must be replaced with conductors of adequate ampacity to ensure safety and prevent overheating. When dealing with parallel conductors, it's crucial to ensure that they are properly sized, installed, and terminated to ensure equal current sharing. The NEC provides specific requirements for parallel conductors to prevent imbalances and ensure safe operation. Before proceeding with any electrical work, it's essential to consult with a qualified electrical engineer or licensed electrician who is familiar with Marina electrical systems and the NEC requirements. They can perform a thorough load calculation, voltage drop analysis, and conductor ampacity verification to ensure that the installation meets all applicable codes and standards. Let's address the specifics of selecting the right size of conductors for the feeders and branch circuits in light of voltage drop considerations. The NEC provides guidance on conductor sizing, but it's crucial to go beyond the minimum requirements to ensure acceptable voltage drop, especially in long runs. First, determine the allowable voltage drop. As mentioned earlier, the NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. For a 240 volt system, a 3% voltage drop would be 7.2 volts, and a 5% voltage drop would be 12 volts. For a 120 volt system, a 3% voltage drop would be 3.6 volts, and a 5% voltage drop would be 6 volts. Calculate the minimum conductor size based on ampacity. Use NEC Table 310.15b16 to determine the minimum conductor size required to carry the load current without exceeding the conductor's ampacity rating. Apply any necessary directing factors for ambient temperature, conduit fill, or other conditions that may affect the conductor's ampacity. Calculate the voltage drop for the minimum conductor size. Use a voltage drop calculator or the voltage drop formula to determine the voltage drop for the minimum conductor size, taking into account the circuit length, current, and conductor resistance. Compare the calculated voltage drop to the allowable voltage drop. If the calculated voltage drop exceeds the allowable voltage drop, increase the conductor size and recalculate the voltage drop. Repeat this process until the calculated voltage drop is within the allowable limits. Consider using larger conductors than required for ampacity. Even if the minimum conductor size is adequate for ampacity, it may be necessary to use larger conductors to minimize voltage drop, especially in long runs. The cost of larger conductors may be offset by the benefits of improved equipment performance and reduced energy losses. Verify the conductor size with a qualified electrician or engineer. Before finalizing the conductor size, consult with the qualified electrician or engineer to ensure that it meets all applicable codes and standards and that it is appropriate for the specific application. Now let's discuss ground fault protection for Marina electrical systems. Ground fault protection is a critical safety feature that helps prevent electrical shock hazards and equipment damage. The NEC requires ground fault circuit interrupters, or GFCIs, for receptacles installed in marinas, as well as ground fault equipment protection, or GFEP, for feeders and services. GFCIs are designed to detect small ground faults and quickly interrupt the circuit, preventing electrical shock hazards. They are typically installed in receptacles located near water or in wet locations. GFEP is designed to protect equipment from damage caused by ground faults. It typically consists of a ground fault relay and a circuit breaker. The ground fault relay monitors the current flowing through the grounding conductor and trips the circuit breaker if a ground fault is detected. The NEC provides specific requirements for GFCI and GFEP protection in marinas, including the types of equipment that require protection, the trip levels, and the installation requirements. It's essential to adhere to these requirements to ensure the safety of people and equipment. When installing GFCI or GFEP protection, it's crucial to test the devices regularly to ensure that they are functioning properly. The NEC requires periodic testing of GFCIs and GFEP devices to verify their functionality. Additionally, it's important to properly maintain the grounding system to ensure that it is effective in providing a low impedance path for ground fault currents. A properly installed and maintained grounding system is essential for the effective operation of GFCI and GFEP protection. Furthermore, let's discuss the importance of proper overcurrent protection in marina electrical systems. Overcurrent protection is another essential safety feature that helps protect electrical circuits and equipment from damage caused by excessive current flow. The NEC requires overcurrent protection devices, such as circuit breakers and fuses, to be installed in electrical circuits to protect against overloads and short circuits. Circuit breakers are designed to trip and interrupt the circuit automatically when an overcurrent condition is detected. Fuses are designed to melt and break the circuit when an overcurrent condition is detected. The NEC provides specific requirements for the size and type of overcurrent protection devices that must be installed in electrical circuits based on the ampacity of the conductors and the characteristics of the equipment being protected. It's crucial to select the correct overcurrent protection devices to ensure that they will provide adequate protection without nuisance tripping. When selecting overcurrent protection devices, it's important to consider the following factors. Firstly, the ampacity of the conductors being protected. Secondly, the inrush current of the equipment being protected. Thirdly, the interrupting rating of the overcurrent protection device. The interrupting rating is the maximum current that the overcurrent protection device can safely interrupt without failure. It's essential to select an overcurrent protection device with an interrupting rating that is adequate for the available fault current at the installation location. Additionally, it's important to properly label all overcurrent protection devices to indicate the circuit they protect and their ampacity rating. This will help prevent confusion and ensure that the correct overcurrent protection device is used for each circuit. In addition to the technical aspects, consider the environmental factors unique to marina environments. Marina electrical systems are exposed to harsh environmental conditions, including saltwater, moisture, and sunlight. These conditions can accelerate corrosion and degradation of electrical equipment, leading to safety hazards and equipment failures. To mitigate these risks, it's essential to use corrosion-resistant materials and equipment that are specifically designed for marine environments. This includes using stainless steel or bronze hardware, epoxy-coated conduit, and watertight enclosures. Regularly inspect electrical equipment for signs of corrosion, damage, or wear. Any damaged or corroded equipment should be replaced promptly to prevent safety hazards. Apply corrosion-inhibiting compounds to electrical connections and equipment to protect them from corrosion. Ensure that all electrical enclosures are properly sealed to prevent moisture from entering. Provide adequate ventilation to prevent condensation from forming inside enclosures. Additionally, consider the potential for lightning strikes in marina environments. Marinas are often located in open areas that are susceptible to lightning strikes. Lightning strikes can cause severe damage to electrical systems and equipment, as well as pose a significant safety hazard to people. To protect against lightning strikes, consider installing a lightning protection system that includes lightning rods, grounding conductors, and surge protection devices. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning strikes or other events. SPD should be installed at the main electrical panel and at individual equipment locations to provide comprehensive surge protection. Regularly inspect the lightning protection system to ensure that it is in good condition and that all components are properly connected. Educate marina personnel and boat owners about the risks of lightning strikes and the importance of taking precautions during thunderstorms. This includes advising them to disconnect shore power cords and avoid contact with metal objects during lightning storms. In addition to these specific recommendations, it's crucial to follow all applicable codes and standards, including the NEC and any local regulations, when designing, installing, and maintaining marina electrical systems. By adhering to these codes and standards and implementing best practices, you can help ensure the safety and reliability of marina electrical systems and prevent electrical hazards. Remember, electricity and water are a dangerous combination, so it's of utmost importance to prioritize safety when working with marina electrical systems. Also, make sure to document everything, including calculations, drawings, and inspection reports. This documentation will be valuable for future reference and for demonstrating compliance with codes and standards.